questions on what we discussed just? No questions. पढ़ा घर जाके किसी ने कुछ? ठीक है. So there is no response. I'll assume everything is fine. We define different types of equilibrium constants, right? K, K, Kf, Kp. They're all definitions, right? And we are going to use these definitions in our analysis for questions. So let us proceed to the next topic. How do we calculate K? Okay. So ये आपने देखा होगा feasibility of reaction. देखा है क्या कभी? When is the reaction feasible? Yeah, feasible. Nobody wants to respond. ठीक है. Let us take this reaction. A times A plus B times B gives L plus M times M. And we know criteria of equilibrium कल देखा था हमने. L into mu of product plus M into mu of M minus A into mu of A and minus B into mu of B is equal to 0. And we know that mu I, chemical potential of component I in solution is RTLN Fi bar plus C. And at standard state, it is mu I 0 equal RTLN Fi 0 plus C. Okay, and if you take 2 minus 3, you'll get mu I minus mu I 0 is equal to RTLN Fi bar minus RTLN Fi 0, which you can write as equation 4. Right? Mu I is equal to mu I 0 plus RTLN AI. AI is nothing but Fi bar upon Fi 0 activity. Okay, any questions on equation 4? So for all the components, we can write equation 4. Mu L for component L is equal to mu L 0 plus RTLN AL. Mu M is equal to mu M 0 plus RTLN AM. Mu A is equal to mu A 0 plus RTLN AA. And mu B is equal to mu B 0 plus RTLN AB. Right? And then we substitute all these equations for mu L, mu M, mu A and mu B in equation 1. Okay. And what we will get is equation 1, mu L into mu L plus M into mu M minus A into mu A and minus B into mu B equal to 0. Can you see this? Equation 5. Okay. So if you substitute this, what you will get is L into bracket mu L 0 plus RTLN AL plus M into bracket mu M 0 plus RTLN AM minus A into bracket mu A 0 plus RTLN AA minus B into bracket mu B 0 plus RTLN AB, and that is equal to 0. Okay. So now we keep certain things on the left hand side, like L into mu L 0 plus M into mu M 0 minus A into mu A 0 minus B into mu B 0 on the left hand side. अब बाकी right hand side में लेके गए हम. What you get is on the right hand side minus L, that is from here, L into RTLN AL minus M into RTLN AM plus A into RTLN AA and plus B into RTLN AB. Okay, so we can take this and put it as power of this term. There is nothing but maths. Because A into ln of AA is nothing but ln of AA to the power of A. Okay, so what you'll get is minus RT ln AL raised to the power of L minus RT ln AM raised to the power of M plus RT ln AA to the power of A and plus RT ln AB to the power of B. You can combine all these terms, 4 terms, and get this right hand side minus RT ln of AL into AL to the power of L into AM to the power of M, because you have taken this out, minus divided by AA to the power of A and AB to the power of B. Any questions on this? Okay, so if there are no questions, L into what you get is ultimately L into mu L0 plus M into mu M0 minus A into mu A0 minus B into mu B0 is equal to minus RT ln AL to the power of L, AM to the power of M, AA to divided by AA to the power of A and AB to the power of B. Equation 6. Right. So we can write equation 6 as, because it is nothing but summation of mu I0 into nu I on the left hand side, and right hand side is same as in equation 6. Okay, any questions on equation 7? So left hand side is nothing but standard free energy change. There is free energy change of reaction when reactants and products are in the same in the standard state, because that is mu I0 standard state we are talking about, and that is nothing but delta G0 for that reaction. So if you put this in equation 7, what you get is delta G is equal to minus RT ln, and this is nothing but K. We have defined K or Ka as that is equal to K. Any questions on equation 8? So if you know delta G0, if we can find delta G0, then we can find the value of K, equilibrium constant. Ultimately, that's what we need in order to find compositions of products and reactants in equilibrium. Any questions on equation 8? बहुत बार equation 8 का derivation आता है exam में, so you should be able to derive this whole equation. This is equation 8.
सर
Yeah.
सर हम डेल्टा जी इक्वल टू समेशन ऑफ म्यू आई इनटू एक्स आई लिखते थे ना, और एन आई समथिंग.
अरे ये अभी किया, कल ही किया हमने. डेल्टा G0 इक्वल टू समेशन ऑफ म्यू I0 इंटू म्यू I. XI कहाँ से आ गया? That was for ideal gases.
यस सर.
ठीक है, और कोई क्वेश्चन है किसी को? Okay. So that is the energy change depends on temperature, because delta G0 depends on temperature. Number of moles of components, each component. यहाँ पर components आएगा यहाँ पर. Standard state specification, we are talking about standard state क्या होगा, and it's independent of pressure at equilibrium. Pressure is not appearing anywhere, it's just a function of temperature. Okay. So let us see what is standard state, how we are defining standard state for this, because we're talking about this delta G0 depends on standard state, right? So for gases, we always define standard state as pure component at temperature of reaction and fugacity equal to 1. This is low pressure. This is always our standard state. शुरू से हमने define किया है when we define fugacity also, right? So ideal gas is pure component at 1 bar. In this case, K is equal to Kf. Right? हमने कल देखा था Kf and K. Right? कहाँ गया? एक मिनट. Yeah. Yes, we have defined, right? Kf equal to K for gases. Ideal gases के लिए Kfi is equal to 1. ठीक है? For ideal gas Kfi is equal to 1, so K is equal to Kf. And we can write delta G0 is equal to minus RTLN Kf. And for solids and liquids, pure solid or liquid at 1 bar and reaction temperature. That's how solids and liquids के लिए define करते हैं. But Kfi is not going to be equal to 1. So only for this ideal gases, Kfi equal to 1, and that's why you get K equal to Kf. ठीक है, any questions? Then let's look at feasibility of reaction. Feasibility of reaction पढ़ा कभी आप लोगों ने केमिस्ट्री में? कल देखा था हमने, right? I think the same question I had asked yesterday also. Somebody had answered. क्या था आंसर? When is the reaction feasible? नहीं याद किसी को?
So del G is negative.
Del G is negative, right? So any reaction will proceed to some extent. And if we talk about any reaction, it may be very small. So if we take water and we say talk about decomposition of water into hydrogen and oxygen, the value of K at 298 Kelvin at room temperature is 1 into 10 to the power of minus 40. Right? And K is defined as pi of AI raised to the power of nu I. That means for this reaction, we can write K is equal to activity of hydrogen into activity of oxygen raised to the power of half divided by activity of water. And when I say 1 into 10 to the power of minus 40, it is almost equal to 0. Okay. So extent of decomposition of water is infinitesimally small at equilibrium. And that's why we say that this reaction is not thermodynamically feasible. Significant होना चाहिए, because this is almost like 1 in 10 to the power of 40. Too small to measure also. Okay. So if delta G0 equal to 0, that is equilibrium condition, कल देखा था हमने, right? If you put delta G0 equal to 0, कहाँ गया? Minus RTL. Right? So if you put delta G0 equal to 0, what we'll get is K is equal to 1. बराबर? If this is
Yes,
equal
sir.
to 0, we'll get K equal to 1.
सर
Yeah.
सर वो दैट इज वाला पार्ट रिपीट कर सकते हैं सर? समझे नहीं सर. थर्मोडायनेमिक फिजिबल वाला.
ये वाला?
यस सर, दैट इज वाला.
किसका वाला?
सर वो दैट इज लिखा है ना, आई डॉट टी, दैट इज.
समझ नहीं आया क्वेश्चन आपका.
एक्सटेंट ऑफ डिकम्पोजिशन, वो वाला पॉइंट नहीं समझे.
Yeah, because we are talking about ये जो है ना, when you say K is equal to 0, that means the activity ऊपर numerator is almost 0. राइट। ये जीरो कब होगा राइट हैंड साइड, के इक्वल टू जीरो कब होगा, व्हेन न्यूमरेटर इज ऑलमोस्ट जीरो, राइट,
Well,
वेरी स्मॉल क्वांटिटी।
yes, sir.
दैट मीन्स ये जो क्वांटिटी ऑफ हाइड्रोजन है और ऑक्सीजन है बहुत कम है, राइट।
Yes, sir.
दैट मीन्स यू आर सेइंग डिकम्पोजिशन जो होना है, और दिस इज डिकम्पोजिशन ऑफ वाटर, राइट, इट इज इनफिनिटली स्मॉल, दैट मीन्स वेरी वेरी स्मॉल, बिकॉज दिस के इज सो स्मॉल। के का वैल्यू हाई रहेगा तो ये ज़्यादा रहेगा एक्टिविटी ऑफ हाइड्रोजन एंड ऑक्सीजन, एंड दिस आर इन अ वे कनेक्टेड टू कंपोजिशन। यानी कितना हाइड्रोजन बन रहा है और कितना ऑक्सीजन बन रहा है, दैट इज इंपॉर्टेंट टू फाइंड व्हाट इज द वैल्यू ऑफ के। और इफ द के वैल्यू इज सिग्निफिकेंट, दैट मीन्स एक्टिविटी ऑफ हाइड्रोजन इज सिग्निफिकेंट एंड ऑक्सीजन इज सिग्निफिकेंट। ठीक है,
Yes, sir. Clear.
okay. So if you take delta G equal to minus RT ln K, and if you say delta G is equal to 0, we have seen that at equilibrium. That means K is equal to 1. K equal to 1 means numerator is equal to denominator, right? Right? If this is equal to 1, then numerator is equal to denominator. The reaction proceeds to considerable extent before equilibrium, right? At equilibrium it is 1. And if delta G0 is less than 0, that means if it is negative, suppose it is negative, right? तो K क्या हो जाएगा? K has to be greater than 0, greater than 1, sorry, because this is negative term. The negative negative निकल जाएगा, इसका negative negative, so you get RT ln K is a positive number. That means K has to be greater than 1. What is ln of 1 equal to, करो ना, कैलकुलेटर है ना आपके पास. What is ln of 1?
0, sir.
0. And ln of 1.1?
0.0953.
That means it is positive, right? बराबर.
Yes, sir.
K will be greater than 0 if delta G is less than, K will be greater than 1 if delta G is less than 0. So then क्या हो जाता है, K जितना बढ़ेगा उतना आपका रिएक्शन बहुत फेवरेबल होता जाएगा. K जितना कम रहेगा, we saw that K was very small here, that reaction was not feasible because K value was very small. So the larger the value of K, the higher is the feasibility, or reaction is more favorable or feasible. Okay, so that means reaction becomes less favorable as delta G0 increases in the positive direction. We want negative delta G0. जितना पॉजिटिव होता जाएगा उतना लेस फेवरेबल होता जाएगा, बिकॉज यू सॉ दैट डेल्टा G0 यहाँ पर 0 लिया था हमने, तो इट वाज ओके. बट इफ यू टेक पॉजिटिव लिया तो इट बिकम्स लेस फेवरेबल, बिकॉज देन इट बिकम्स K बिकम्स वेरी स्मॉल. दिस इज
मतलब
पॉजिटिव.
सर नेगेटिव से पॉजिटिव ना, नेगेटिव से पॉजिटिव जाएगा तब.
डेल्टा G0 पॉजिटिव रहेगा तो इट बिकम्स लेस फेवरेबल, डेल्टा G0 नेगेटिव रहेगा तो दैट इज व्हाट इज
सर
feasibility कंडीशन ना.
अगर डेल्टा G0 पॉजिटिव होगा तो रिएक्शन पॉसिबल ही नहीं ना.
होता है पॉसिबल, आई विल सी दैट कंडीशन ऑल्सो. ऐसा हम सी जनरली एक ब्लैंकेट स्टेटमेंट दे देते हैं केमिस्ट्री में या अर्ली स्टेजेस में कि when delta G0 is positive it is not feasible. No, it is feasible, but it is not feasible at 298, because when you say delta G0 we're talking about standard state, which is normally 298 Kelvin. That's how we
Okay.
define standard state generally, right? At 298 it may not be feasible, but it will be feasible at some other condition. We'll see that. ठीक है. So as delta G0 increases in the positive direction, reaction becomes less favorable. But many reactions with delta G is equal to positive are feasible for industry point of view. Because in industry, it's not that every reaction takes place at 298 Kelvin. Temperature as 1000 degrees centigrade are available or used. So temperature change कर तो delta G change होता है, delta G0 नहीं, delta G at that reaction temperature will change, and that is what makes it feasible. Okay. So let's take an example: methanol synthesis. CO carbon monoxide plus hydrogen gives CH3OH, and delta G0 is plus 46,000 at 600 Kelvin. Okay. Now this reaction is feasible at high pressure. Pressure change किया इसका. See, there are many factors because we talk about what you call low pressure atmosphere or 1 bar. That was our operating standard state definition. But many reactions are taking place in industry at very high pressure and very high temperature, because that's where they become feasible. At lower temperature, lower pressure, they may not be feasible. Okay, so based on experiments or based on data from industry, these are the criteria which we can define for feasibility. Right? If delta G0 is less than 0, reaction is promising. Yes, ये general statement हम बोलते थे. It's what you have been looking at, you have been seeing so far. Chemistry में देखा होगा. But based on data, you can generalize that between 0 to 40,000 plus 40,000, reaction may or may not be possible but needs further study. So that means we need to find out at the reaction condition, जैसे टेम्परेचर चेंज होता है, प्रेशर चेंज होता है, व्हाट इज द वैल्यू ऑफ प्रेशर का इफेक्ट नहीं देखा था हमने, राइट? बट टेम्परेचर चेंज से वी कैन फाइंड आउट व्हाट इज वैल्यू ऑफ जी एट दैट रिएक्शन टेम्परेचर, एंड दैट मे बी feasible. And delta G greater than 40,000, reaction is very unfavorable. यहाँ पर बोलता है जनरल स्टेटमेंट, राइट? बट ये देखा हमने यहाँ पर 46,000 के लिए भी इट इज feasible. So there are guidelines, they are not laws. ये ऑब्जर्वेशन के बेसिस पर है, एंड ऑब्जर्वेशन इज essentially based on experiments और इंडस्ट्री में क्या होता है. So these are just guidelines for reaching to some conclusion. अगर इतना है तो then we need to do some processing. That means we need to find out delta G at that condition which we are evaluating, and then see whether it is negative or not. ठीक है? Any questions on criteria of feasibility? So next year you are going to do a B project, and when you do evaluation of feasibility of a reaction, you may find that at standard state, delta G0 is positive. They need to find what is delta G0 at reaction condition, and that may turn out to be negative. We'll see how to do that. Okay. 3,000, 5,000 psi, that is very high pressure. K values are significant. 1.5 10 to minus 3 is not that bad, and it is feasible. So if you change pressure, if you change temperature, a feasible reaction which is not feasible in standard state of what we define as 1 bar low pressure may become feasible at high pressure and high temperature. Okay? So this is feasible, and react yield is almost 50%, which is quite good from industry point of view. Any questions on feasibility of reaction? Okay, if no temperature, no question, then let's see what is the effect of temperature and equilibrium constant. ली चार्टले प्रिंसिपल पता है लोगों को? What is ली चार्टले प्रिंसिपल? पढ़ा है आप लोगों ने? Anybody remembers ली चार्टले प्रिंसिपल? नहीं पढ़ा है, केमिस्ट्री में पढ़ा होगा ना?
Yes, sir.
What is it?
I do not remember.
चार्टले प्रिंसिपल किसी को याद है?
सर वो अगर प्रोडक्ट ज्यादा हो गया तो उसको निकाल के हम रिएक्शन फॉरवर्ड डायरेक्शन में कर सकते हैं, मतलब
Yeah,
रिएक्टेंट या प्रोडक्ट
that
निकाल
is
के।
one application of Lee-Chatterley's principle. Yes, you can use it that way. But what is Lee-Chatterley's principle? What does it say? Statement या कुछ भी उसका understanding, not exactly exact words. नहीं याद किसी को? ठीक है, let's see. So Lee-Chatterley's principle says a system at equilibrium, if it is subjected to a disturbance, disturbance could be in terms of pressure, it could be temperature, it could be anything, right? Responds in a way that tends to minimize the effect of disturbance. Right? अगर pressure बढ़ाया so it will respond in a way trying to reduce the pressure. Temperature बढ़ाया, it will respond in a way that will try to reduce the temperature. Right? That means increase in temperature will shift equilibrium direction of heat absorption. Reduce temperature reduce करना है ना, heat absorb होगा, right? Temperature बढ़ा है, heat release हो रहा है, बराबर? When you say exothermic reaction में heat release होता है, endothermic reaction में heat absorb होता है, right? You know this concept? Endothermic, exothermic, right? So when you say reaction is exothermic, जैसे हमने देखा था पीसी में कि suppose we have combustion of fuel, coal बोलो या कोई और fuel बोलो, if you take say butane, उसको burn किया, जैसे अभी LPG होता है घर पे, right? So when you burn LPG at home, heat is released, and that is how you cook your food. So that is an exothermic reaction. It releases heat, right? So that is delta H is क्या होता है, पॉजिटिव होता है नेगेटिव होता है एक्सोथर्मिक रिएक्शन में? व्हाट इज साइन कन्वेंशन?
Negative.
Negative. So when we say exothermic reaction, by when you say heat of reaction, if you look at heat of reaction, it is minus something, that indicates that is the exothermic reaction, that reaction is going to release heat, which you can use for some purpose, right? Endothermic reaction is opposite of exothermic, right? That means we need to supply heat, it absorbs heat, right? So we need to supply heat for that reaction to occur, right? So for example, increase in temperature will shift equilibrium direction of heat absorption, right? So equilibrium will shift in endothermic direction if temperature is increased, because endothermic reactions absorb heat, right? जैसे अभी हम कोई रिएक्शन ले रहे हैं जो एंडोथर्मिक है, right? Suppose that 100 degree centigrade reaction is occurring, it's endothermic reaction. That means we have to supply heat because that is absorbing heat. तो जितना टेम्परेचर बढ़ाएंगे उतना रिएक्शन बढ़ेगा, right? That means what you are saying is it is absorbing heat by in opposite direction, right? Temperature increase, reduce the temperature, absorb endothermic reaction. और दूसरा exothermic reaction बोला तो exothermic is releasing heat, right? This right, releasing heat यानी अगर जो रिएक्शन हो रहा है तो टेम्परेचर बढ़ेगा रिएक्शन मिक्सचर का, राइट? जैसे अभी हमने एलपीजी लिया, राइट? एलपीजी का टेम्परेचर रूम टेम्परेचर रहता है, बट व्हेन यू बर्न इट द टेम्परेचर इंक्रीज टू से 500-600 डिग्री सेंटीग्रेड or 400 degrees, whatever it is. That means it is releasing heat. That means the reaction mixture is becoming hotter. Right? So higher temperature will, what will happen is it will shift reaction in lower direction. अगर टेम्परेचर रिड्यूस करेंगे बिकॉज इट इज रिलीजिंग द हीट, राइट? तो उसका उल्टा इफेक्ट होगा. टेम्परेचर रिड्यूस किया तो एक्सोथर्मिक रिएक्शन ज़्यादा होगा, एंडोथर्मिक रिएक्शन को हीट सप्लाई टेम्परेचर बढ़ाया तो ज़्यादा होगा. समझ में आ रहा है? So endothermic reaction is favored by increase in temperature because this increase in temperature supplies heat. And endothermic reaction absorbs heat. Because the reaction itself needs heat for it to be conducted. That higher temperature, this is opposite, right? ये absorption of heat है, ये supply of heat है, this उल्टा है. Similarly, exothermic reaction, it releases heat. So when we decrease the temperature, that means we are removing heat, right? समझ में आया? Any questions, doubts on this example of endothermic and exothermic reaction?
Clear, sir.
Okay. So increased temperature favors exothermic. Okay. Increased temperature favors reactants. This is the difference, right? So when you say A goes to B and a reversible one, and you say this is exothermic reaction. Right? So temperature बढ़ाया तो that means it will go in the other direction. If this forward direction is exothermic, reverse direction is endothermic. By principle, by logic, अगर forward direction, that means if I say CH4 plus oxygen and it gives you CO2 plus water, this is exothermic. Reverse reaction is always going to be endothermic. Right? So when I say increased temperature favors reaction, that means उल्टा reaction हो जाएगा, because increased temperature में actually ये endothermic reaction होगा, and products in endothermic reaction. Products in endothermic reaction is ये product है, right? Reactants है, यहाँ पर ये products है, right? So exothermic reaction का जो है increasing temperature will favor reactant means उल्टा reaction होगा, reverse reaction होगा, powered reaction नहीं होगा. Is this clear? Any questions? If there is no question,
हेलो सर.
क्या बोला?
हाँ सर, मतलब ये जो क्राइटेरिया है सिर्फ हम रिवर्सिबल रिएक्शंस के लिए लगा रहे हैं क्या?
नहीं, रिवर्सिबल रिएक्शन मैंने एग्जांपल दिया मैंने. Doesn't matter if it is forward reaction, doesn't matter. Suppose this is A is close to B, right? And ये irreversible reaction लिया मैंने. Suppose this is exothermic. That means I should operate at low temperature if I want to get product. अगर endothermic रहेगा, then I should operate at high temperature. That is the principle. Because ये जो बोला ना कि exothermic reaction releases heat, that means अगर reaction हो रहा है तो already reaction product will become hotter. That's why you need to keep temperature low. Endothermic reaction, that means it absorbs heat, so actually we need to increase the temperature or supply heat. That's what it is. ये example था reversible का, reversible में same रहेगा. एक्सोथर्मिक के लिए you need lower temperature, endothermic के लिए high temperature.
Okay, sir.
Okay. So now let us see what is the effect of temperature on equilibrium constant. Because ultimately that's what we want to see. And we know that delta G0 रहेगा equal to minus RT ln K. So equilibrium constant का अगर हमारे को temperature effect मिला तो delta G0 का भी effect मिल जाएगा. So we start with Gibbs-Helmholtz equation which we had derived before. Dou by T by dou T at constant pressure is equal to minus Hi by T square. And at standard state this becomes dGi0 by T by dt at constant pressure equal to minus Hi0 by T square. Now equation 2 is total derivative. Since free energy depends on temperature, we have seen that, not pressure. You can take a total derivative. So multiply equation 2 with nu I and add for all species because we want to find for a reaction, right? So we say d of summation nu I gi0 by t. That means we are multiplying this term with nu I, that is stoichiometric coefficient, and summing it for all the reactants and products. Divided by dt is equal to minus right hand side में same करना पड़ेगा summation of nu I into Hi0 by t square. Okay, and we know that dou G0 is nothing but summation of nu I gi0. ये याद है आपको? We had seen that, right? When you look at PC में देखा था क्या था? Heat of reaction. Heat of reaction क्या था? Suppose I say A plus B gives C.
Heat of product.
Right? So it was essentially delta H of formation of C plus delta H formation of D delta formation of A minus delta H formation of B. It is nothing but summation of nu I delta H formation of I. Right? ठीक है, याद है ये? So same thing we are doing here. If you want dou G0, you have to take again summation of nu I into Gi0, and delta H0 is nothing but summation of nu I into Hi0. And that's how we always do for heat of reaction, heat of formation, वगैरह वगैरह. So substitute 4 and 5 in equation 3, and what we'll get is essentially d of delta G0 by t divided by dt is equal to minus delta H0 by t square. This is nothing but ये हो गया delta H0, ये हो गया delta G0. Okay, so divide left hand side, right hand side by r, and what we get is d of delta G0 by RT. अंदर ले लिया कांस्टेंट ये वो r divided by dt is equal to minus delta H0 by RT square. And you know that delta G0 is equal to minus RT ln K. So if we substitute equation 8 in equation 7, what you get is this term is delta G0 by RT is ln K minus ln K. ये minus minus plus हो गया, and what you get is d ln K by dt is equal to delta H0 by RT square. And this is called Van 't Hoff equation. So if you know heat of reaction, then we can find what is the effect of temperature on K. Any questions on equation 9? ठीक है, इक्वेशन 9 भी डेरिवेशन आता है एग्जाम में, Van 't Hoff equation derivation. Okay, so delta H0 is nothing but standard heat of reaction, and if delta H0 is equal to constant, we can integrate equation 9 from T1 to T2, and where K has value of K1 to K2. What you get is ln K2 by K1 is equal to minus delta H0 by R 1 upon T2 minus 1 upon T1. So if you know delta H0 and one K value, you can find what is the second K value. So all we need is one K value and the heat of reaction, then you can find what is the K value at some other temperature. Any questions on equation 10, 9 and 10? If there are no questions, let's proceed further. Okay, so now let us see what is the effect of temperature on standard heat of reaction. याद है किसको हमने किया था पीसी में? किया था कि नहीं किया था? यूनिट 5 में एनर्जी बैलेंस में किया होगा. याद आ रहा है? नहीं आ रहा है? Hess's law.
Yes, sir.
We start with Hess's law. It's just a revision of that. The net heat evolved or absorbed delta HR in a reaction is the same if the reaction takes place in one step or multiple steps. ये देखा था हमने. Okay. Or you can say in going from a particular set of reactants to a particular set of products, the change in enthalpy is same whether the reaction takes place in one step or in a series of steps. Right? एक रिएक्शन लिया, दो रिएक्शन लिया, तीन रिएक्शन लिया, अगर रिएक्टेंट्स और प्रोडक्ट सेम है तो सम ऑफ दोस रिएक्शंस इज heat of reaction or single reaction. And we have said that Cp we are going to take it as उस समय A plus Bt plus Ct square लिया था. यहाँ पर because book is using this, I use this alpha plus beta T plus gamma T square, doesn't matter, just constants है ये. Calculate standard heat of reaction at any temperature from heat of reaction at standard state. Why we take standard state? Because these are readily available. Tables are available which give heat of formation at standard state. और heat of formation standard state है तो you can calculate heat of reaction at standard state from tables. कुछ करने की जरूरत नहीं है. Okay. So what we are going to do is take reactants at reaction temperature T, and we want to find what is the heat of reaction at that temperature T, delta HT. Products are at temperature T. So what we do is we go from temperature T to T1, which is now standard state. That means we are cooling it. अगर ये high temperature है तो इसको 298 तक लेके आएंगे. T1 is essentially 298. So we cool it. Reactants at T1 मिलेगा, and this is what is heat of enthalpy of cooling reactants. Then we take standard heat of reaction at temperature T1, which is 298, which is available from tables, delta H2. So we get products at temperature T1, which is 298. And then we heat the products to the desired temperature, which is reaction temperature T. So essentially it is enthalpy of heating products, which is delta H3. So if you know delta H1, delta H2 and delta H3, we can find out delta HT. Okay. So step 1 is reactants are cooled from T to T1. So delta H1 is nothing but summation of integral T to T1 Ni Cpi dt, right? N Cp dt, right? अगर ये मोलार है Cp, mole joules per mole, so you get Ni. If it is mass, then we mCp dt. So nCp dt integrate from T to T1 and sum it for all the reactants. So what you can see is this is nothing but Ni is nothing but nu I, कितना reactant stoichiometric number है. So it becomes same thing T1. What we are doing is nu I Cpi dt, right? Because now nu I is negative for reactants, right? के लिए पॉजिटिव रहता है, रिएक्टेंट्स के लिए नेगेटिव रहता है. So इसको हमने लिमिट चेंज कर दिया. Because this T to T1 इसको T1 to T कर दिया. समझ में आए कैसे लिमिट चेंज किया? Okay. So nu I is positive for products and negative for reactants. That's why we are changing the limit. Then step 2 is this thing, standard heat of reaction at temperature T1, which is 298. which is available from tables. And then step 3 is heating the products from T1 to T. So delta H3 is equal to summation of integral T1 to T Ni Cpi dt. Now this is for products, right? So we can write this instead of Ni, we can write nu I, stoichiometric number. Limits will remain same because it's now positive. Nu I is positive for products. So we are now going to change the limits. Limit will remain the same. Okay. So now if you want to add all these things, you will get delta H at temperature T. Delta H0 is equal to delta H1 plus delta H2 plus delta H3. Right? ये ले लिया हमने. We are just substituting this summation for reactants T1 to T, integral T1 to T, nu I Cpi dt plus delta H T10 plus summation over products T1 to T nu I Cpi dt. And we can combine these two and we get delta H T10 plus integral T1 to T summation अंदर लिया nu I Cpi dt. ठीक है, लिमिट सेम है. You can add these two reactants and products. Any questions on equation 2? Okay. So when you substitute equation 1 and equation 2, equation 1 was essentially Cp. Equation Cp is equal to alpha plus beta t plus gamma t square. We substitute both this in equation 2 and we'll get integral T1 to T nu I summation over nu I into Cp अगर डाला alpha I plus beta I t plus gamma t rt square into dt, right? And this will become summation nothing but nu I open किया इसको, equation 3. Now we define delta Cp is equal to delta alpha plus delta beta t plus delta gamma t square. Whereas delta alpha is nothing but summation of nu I into alpha I, and delta beta is equal to summation of nu I into beta I. Delta gamma is equal to summation of nu I into gamma I. Then equation 3 will give delta ht0 is equal to delta ht10 plus integral t1 to t delta cp dt. So by this definition of delta cp and delta alpha, delta beta, delta gamma. Any questions on equation 5? Okay. So then we integrate this equation 5 to get delta ht0 is equal to delta ht10 plus delta alpha. Delta cp is nothing but delta alpha, right? Plus delta beta t plus delta gamma t square. So delta alpha into integral limit t1 to t है. So t minus t1 हो जाएगा. Plus delta beta by 2 t square minus t1 square and delta gamma by 3 t minus t cube minus t1 cube. Any questions on equation 6? Okay. So then if you look at equation 6, T1 is a constant, right? 298 is also constant. Is also constant, right? So you can combine all these terms into another constant called delta H1 combined with this one also is also constant. And what you get is delta T0 is equal to delta H prime plus delta alpha into T plus delta beta upon 2 T square plus delta gamma upon 3 T cube. सब कांस्टेंट टर्म्स को एक नया कांस्टेंट बना दिया डेल्टा एच प्राइम. Any questions on equation 7? So now if you look at the equation 7, you need to find this constant. So for this, if you have one value of delta ht0, that means 298 पर अगर पता हमारे को ये, so we can find out what is the value of delta h prime, right? And this is normally available, so we can find out value of delta h prime from one value of delta ht0 and then use it to find delta h at any temperature. It may be 500, it may be 600 Kelvin, 700 Kelvin, जो भी temperature है. You can find delta H at heat of reaction at any temperature. Once you know this, delta H prime. Any questions on this? It's just a revision from PC. पहले का किया हुआ है, nothing new, but okay. Next we'll see tomorrow. What we want to see is effect of temperature on equilibrium constant. वो कल देखेंगे. But we'll start from here. This is the starting point for that. So Van 't Hoff equation देखा था हमने, right? K is related to delta H. So once we know this thing, we can find out what is the effect of temperature on equilibrium constant also. Any questions? Okay. So next week, I am going to take CPT lecture on Monday morning, 9 to 10, and CPT lecture on Tuesday also from 11 to 12. क्योंकि आपका CPT का सिलेबस ऑलमोस्ट कंप्लीट हो गया, थोड़ा बचा है. तो थर्सडे फ्राइडे को आपका CPT होगा. Monday, Tuesday I'll take thermo. Because we need to do 2 units. I want to finish before Diwali. ठीक है, तो आपके कैलेंडर में देखिएगा, आपको CET2 मिलेगा आपको मंडे मॉर्निंग के लिए एंड ट्यूसडे के लिए. मेरी बात हो गई नानी वाड़कर सर से, HOD से बात हो गई है. बोथ हैव एग्रीड एंड आई विल टेक दोस 2 लेक्चर्स मंडे एंड ट्यूसडे टिल दिवाली. Any questions, comments, suggestions? Okay, there are no questions. Let's stop here.